You guys hear me all right? All right, cool. How's everybody's week going so far?
It's going okay. The Learn Smart was kind of difficult. I don't know. Some of the concepts are kind of tough to wrap my head around.
I'm sorry, I missed the first part of that because my sound was really low. Julian, what class are you talking about?
Oh, I mean, for this class,
Learn
for
Smart?
the Learn Smart,
Yeah,
I went ahead, I did it, and
cool.
I don't know. It's kind of difficult for me. I didn't really understand it that much.
Well, we'll go through that stuff. I mean, I asked you guys to do it ahead of time. That's kind of part of it, just so you can kind of start wrestling with some of those ideas beforehand and maybe ask some good questions instead of reading it like later and still being confused.
Yeah, because I mean, I know it is a continuation of the last class, MET, um, but it's just like starting right off the bat. I mean, with all these like unit vectors and stuff relating to that.
Okay, yeah, we'll go through some of that today. Most of the stuff in that reading is not stuff like the calculus review is as extra that um isn't really in the book. You guys, other classes going all right? Yeah,
For the most part, yeah.
cool.
It's kind of weird because I have one of my classes which has like a whole bunch of work due Sunday, but then he's told us like, hey, some of that's wrong. I'm gonna change that like later when I get time. And I'm like, oh, that's cool, but like I kind of need to know which ones are due.
Are you
Yeah,
talking about EET?
yeah, he
Yeah,
said
yeah.
sometime later.
Nothing's due this weekend.
Oh, nothing's
That's
due.
what
Nothing's due this
that's what he said. I think. Yeah,
Yeah.
including for the lab.
He
Yeah.
hasn't
But
changed
putting
anything
stuff on
yet.
Tuesday and Wednesday. I think.
Well, that just saved me a lot more time. Then perfect.
Yeah, nothing's changed in Loud Cloud, so that's fun.
He said he was gonna change it sometime today, but
Knowing it is only like 1:30, so fair enough. Or sorry, 12:30.
12:30.
Yeah, I'm really confused about the time because I'm on Eastern
Yeah.
time. So every time someone says the time, I'm like, what?
Yeah, these time zones have been so much fun.
Especially when Arizona doesn't do daylight savings.
Oh yeah,
I feel like we should all convert to not doing daylight savings.
I would be fine with that. Honestly,
Agreed.
100% fine with that.
No benefit to doing it.
Well, there was a benefit years ago, just not now.
It's pretty helpful when you live really far north, like up in Canada, especially because it'll get bright at like the sun will come up like 4 a.m.
Yeah,
So it is kind of nice where it's like, oh, now it's at 5 a.m. instead of 4 a.m. that the sun's coming up. So that's like a little bit better, but I kind of get it.
I mean, but that's kind of how it works, like all the time. Like over here, like sun's setting at like 7-ish, when before it was normally we were like 8-ish. It's kind of like it always happens. So I don't know.
fair enough.
Yeah, and like, yeah, it's kind of weird how that works because like when you get to winter where I am, it's like it's completely opposite, and we're at the point where it's like sun rises at like 6 or like 7, and then sets at like 4:30.
All right, guys, let's get rolling, shall we? It is it's time. Yeah. Lord, thank you for bringing us together this afternoon. Thank you for getting us through that first week of online mess. Pray that you would help us get through the next couple, that you would just continue to bless us, help us to get a good weekend in, do some things for us, but also get all of our work done. In your name we pray. Okay. So we are back, right? We're back at it. I know you're all super excited because why wouldn't you be? This is probably the most exciting part of all your days. It's the
Obvious.
Avi. Yeah. All right. So today, what are we doing? We're gonna start the slides, maybe. All right. So just so you guys know, you might see at the top here, right? It says it's recording, right? We talked about that last time, but this time it says live, right? And this is gonna make it easier for me to get this on YouTube in a fast manner. So it is streaming directly to YouTube right now as we speak. It is on a private thing, so nobody else can come in and see it. When you come back later, you'll be able to watch it, and that'd be great, right? It'll look exactly like the last video I put up, which is just the Zoom stream with the camera up in the top, and you can see all of the slides, right? I don't know if I'm going to be able to write on this today. I'm going to guess probably not. So I'm going to try to use this whiteboard here when we do example problems, right? I don't know how good it's going to be. It's pretty bright. Let's see. That's not going to help. I might have to turn some lights off to get some of the glare off here, but we'll figure that out as we go. Figure that out as we go. All right. All right, so everything was confusing, right? Online part, integral, difficult. All right, so the integrals and derivatives are an ends to a means here, right? We need to use these as tools, right? Some of the ones that we did in class are definitely more difficult than what we're going to be seeing in the upcoming classes. What we're going to really be doing is you're really going to have to be comfortable more so with the idea of taking a derivative than doing an integral. We're probably not going to do integrals all that much. But you know, if we do, it's going to be simple like polynomials, nothing that's being divided by anything. So you'll have stuff like x squared plus x plus 7, or you know, maybe a cubed function like 7x cubed plus 25x squared, right? Stuff like that. So taking a derivative or an integral of that, and you'll be given all of the time intervals that you need to do things over and things like that. 6. Where's that 9? I can't tell. It's on its side. G. Maybe it's a G. I don't know. The online part. Yeah, this is going to be online until you guys come back to class. So after this week, we've got 2 more weeks where you're online. In week 4, you all just come into the class, and this is a normal thing. We'll do it on the screen, right? And everything will be great. Everything will be great. All right. Let's see. Is there anything else? Zoom, solve. Everything in the class is confusing. Well, I hope that we can get into some of the dynamics, the actual dynamic stuff today, which we will. And hopefully you guys will not think that that's too bad, especially since some of the book stuff will be there, right? Do you guys have any other pressing questions from last class? Anything that related to this that you think I need to bring up right now? Is everybody otherwise okay? Yes, no.
So I know you had put a thing on the Discord server. I haven't really worked with Discord much before, honestly.
Mhm.
And I know it's really weird in my age group. And I guess I was kind of curious, like, so if I try to access it, is it like something that's like always running, or is it like certain times, or like how does it work?
Discord servers just run continuously. You can always post to it. Think of it, it's just basically like a chat room that you have access to. So you can post questions or things there, and other people in the class can see them. They can respond to them if they want. We've got 2 chat rooms in the server. One is for class-related stuff, and one is for whatever the heck you guys want to talk about. I'm not gonna micromanage it, and, right? Obviously, if people are being disrespectful to one another, that's a problem. But as long as we play nice, there's no reason why we can't have a Discord server. There's a voice channel on there too. If you guys want to use that to, like, for voice chats, you can do that. Right.
I had a quick question.
Yeah.
For the Learn Smart homework, do you want us to submit anything in LoudCloud or just leave it?
You don't have to. If you want to, you can, but you don't have to.
Okay.
It's done in McGraw-Hill. Like, once it's due in LoudCloud, I go into McGraw-Hill and I just check to see what the grades are, and then I put them in the LoudCloud. So.
Okay.
Once it's done, it's done. You don't have to do anything else. I don't think I mentioned this last time, and I want to mention this to you guys now. This dynamics class is not different than the one that we teach for mechanical engineering and the other engineering courses. Okay, so it's not different. These are the same problems. This is going to be the same topics, right? It's the same content. So I just want you to keep that in mind. I'm not trying to scare you off. I'm not trying to do any of that. We're going to take it slow. We get significantly more time in this class to discuss these topics than we do in ESG 360. But I just want you guys to be aware that the content is the same. Okay. I've taught this class a lot, and I'm hoping that I can answer any and all of the questions that you guys might have. Okay. All right. So these things are due, right? Lab safety waiver. I've heard that some people are having issues with lab safety waivers. Is this true or false? Or some of my other students have been reporting issues. I wonder if that's just on an individual basis or whatnot. If you have an issue with the lab safety waiver, contact the help desk and let them know. But it doesn't seem like you guys are having issues with it. So we have our Learn Smart. That's due tonight, right? So please do it before the end of tonight. It shouldn't take you that long. I know some of you guys have already done it, right? And we'll probably vouch for the fact that it's not super intensive to get that done. And then the homework one is due on not this Sunday, but a week from Sunday. Okay. Any questions on the assignments that are due for topic 1? No. Trying to figure out the best way to see all you guys. Okay. Cool. I guess not. So what are we doing today, right? We're going to talk about rectilinear motion, right? So remember, this is motion in a straight line. We're going to learn how to determine the motion of a particle, and we're going to talk about uniform rectilinear motion, right? So that means when we have acceleration that is constant, right? Constant acceleration. That's what makes it uniform. So there's going to be a bunch of definitions today. Okay, let me get this. I gotta get this in a good spot. That'll be good. Nope. Sorry, I'm still trying to play around with Zoom positioning of stuff. There we go. All right, so what is rectilinear motion? We talked about this a little bit last class. We saw the picture of that Batmobile looking car, right? Rectilinear motion refers to a particle moving along a straight line, right? It's honestly, rectilinear motion is probably the simplest form of motion that we're going to talk about. And in kinematics, the easiest, right, we've taught, you've probably seen this in physics and whatnot, but distance is equal to rate times time, right? That's a kinematic equation. We can understand how far we've gone by talking about how fast we were going and how long we were going for, right? That describes the motion in a straight line. We have position coordinates, right? So defined by a positive or negative distance from a fixed origin on a line. Position, velocity, and acceleration are what we refer to as vector quantities, right? And a vector has magnitude, right, or size, and direction, right? So it's going to be positive or negative, and that's based off of which way we've defined as positive. Typically, you'll see a coordinate system, right, which has positive is up and to the right, right? That's typical. Doesn't have to be. You can choose it however you want. But just remember, the positive and negative refer back to our coordinate system. Motion of a particle is known if the position coordinate for a particle is known at every value of time, or t. And we can express this in the form of a function, right? For our example here, we'll have x is equal to 6t squared minus t cubed. So if time was equal to 0, right, then we would say that x is equal to 0 here, right? Because 6 times 0 squared is 0, minus 0 squared is 0, or 0 cubed is 0. So we'll get 0. Okay, and if you plug in time points, right, you can come up with a table, and you could plot this if you wanted, right? So I guess I should have brought those in as we were talking, right? So this top drawing here shows just rectilinear motion, right? We started at O and we moved by some distance x to point P, right? We could also move negatively, right? You can move to this P prime point, and that would be a negative motion, right? And here's our curve, right? This is the curve described by 6t squared minus t cubed, right? So if you went into Excel, right, and you input that into your first cell, right, or you put that in a cell and you kept referring it back to, and you drag the formula down as you increase the time, right? You would get this plot. You would be able to plot this. Right? All right, so far so good, right? That's position. Right? I think we're all pretty comfortable with the idea of position, right? And it's just where we are in space. Just where we are in space. All right, so let's talk a little bit about what happens if we're talking about our particle here, P, again, right? And it's going to start at this point O, right? And I say that, you know what, it's going to move by some position X, and that causes, that happens over some amount of time T, right? But then it moves a little bit more, and that new distance, we're going to call that delta X, and it takes a little bit more time, which we call delta T, right? So the entire thing, right, moves by X plus delta X in time plus delta T, right, and T plus delta T. Okay, so we can define the concept of a velocity, which is telling us how quickly we are moving position, right? How fast are we changing our position in time with respect to time, right? And the average velocity is the change in X divided by the change in T. And I'm hoping that you guys kind of see some parallels here from that video that we watched last class when we were talking about derivatives, right? Because how do we define the derivative? Well, we take the limit as time goes to 0 of the change in X over the change in Y. In this case, the change in X over the change in T, right? Or sorry, the change in Y over the change in X over T, right? Okay. So the derivative of position is velocity, right? So if we use the example that we had on the last slide, right, where we use 6t squared minus t cubed, and I took the derivative of that, right, I would get the instantaneous velocity, right? Instantaneous velocity, I would get an expression for the velocity from which I could find the instantaneous velocity, right? The average velocity is saying, well, over this time period, I'm moving about this fast, right? On my way to work, I averaged 60 miles per hour today, right? That's my average velocity. But at certain points along the way, at certain time steps, I can figure out my instantaneous velocity, right? So at a specific time, I was traveling this fast. That's instantaneous velocity. Velocity is a vector, right? And can be positive or negative, okay? It can be positive or negative. If we're just talking about how much velocity we have, we don't care which direction it's moving in. We consider that to be the speed, right? That's the magnitude of my velocity vector is my speed. Okay, so if I take the derivative of my example from the last time where x is equal to 6t squared minus t cubed, right? Take that derivative there. I'll end up with velocity equation, right? Which is 12t minus 3t squared. Right? And just to refresh, right? How do we take the derivative of this? Well, take the 2 down, right? That's 2 times 6t to the 2 minus 1. Take the 3 down, 3 times t to the 3 minus 1, which is why we're left with 12t minus 3t squared. And again, you could plot that. If you did a graph of that, you get something that looks like this. Okay. You guys have any questions on velocity right now? No? Again, this is probably, some of this is probably review from like your physics 1 class, I would guess, right? Probably. So the next thing we'll talk about is acceleration. Right, so we talked about position, and then we said, you know what if position changes as a function of time, and that turns out to be the velocity. Well, now let's talk about what happens if the velocity changes as a function of time. What happens then? Well, that's when we get the acceleration, okay? So acceleration, well, we have this definition again, and as we saw last time, that means that we're just taking the derivative of the velocity, right? There's a couple of cases that we can talk about here, right? And this is where acceleration gets a little bit tricky in a sense, right? So I can have positive acceleration if I have increasing positive velocity, right? So if you look at this picture that accompanies this statement, right? If my velocity is increasing to the right, which is positive, right? We're assuming that everything moving to the right is positive here. Then my acceleration would also be positive, right? Or I can have decreasing negative velocity. So if I have velocity that's moving to the left, but it's decreasing, that also gives me a positive acceleration. And that's the one, right? So what does a decreasing negative velocity mean? Right? Well, it means that I'm slowing down, moving to the left, right? So I would have a positive acceleration because remember, acceleration, velocity, and position are vectors. So the direction is important, okay? So there's two cases where we can have positive acceleration. So your acceleration doesn't have to be in the direction of your velocity, right? It doesn't. We're talking about the rate of change of the velocity. Which direction is my velocity changing in, right? Are we getting a positive change or a negative change? Similarly, we can have negative acceleration when we have decreasing positive velocity. So I'm slowing down, right? This makes sense, right? I'm driving my car, I hit the brakes, that's going to apply a negative acceleration, right? I will be slowing my velocity moving forward, right? Sometimes we call a negative acceleration a deceleration, right? It's the same concept. But we can also have increasing negative velocity. And that would also be a negative acceleration. So it doesn't always, so the difference here is what, right? A decreasing positive velocity is a deceleration. An increasing negative velocity means I'm speeding up in the other direction. All right. This means I'm going to be traveling faster to the left. All right. So just be aware, right? Be aware of these distinctions. They don't really come into play too much with the particle stuff that we're going to talk about here, but they're important to see, right? So again, we're gonna use our example from the last two slides, right? This time I've got my velocity equation that we came up with last time was 12t minus 3t squared. And if I take the derivative of that, right, take the derivative of that, we'll get 12 minus 6t. And I can plot that, right? And that's just gonna be a straight line that looks like that red graph. All right, is everybody all right with that? You guys are in luck. I brewed coffee right before this class, so I'm gonna be like energy ramping up as we go. It's gonna be great. It's gonna be great.
Wish I did. Sounds great.
All right. Okay, so that's acceleration, right? So let's quick show of hands. You can throw your answer in the chat. How about that? Why don't we do it that way? That'll be an exciting way to interact here, right? So what is true about the kinematics of a particle? A, the velocity of a particle is always positive. B, the velocity of a particle is equal to the slope of the position time graph. C, the position of a particle is 0, then the velocity must be 0. And D, if the velocity of a particle is 0, then its acceleration must be 0. Which of these is true?
Is B true? Pretty sure it is. Right?
I'm
I
the
don't know. Is it the other way around?
one asking the question. All right, so in the chat, looks like we got answers from most everyone, right? Everybody's going with B, feeling strong. It's B. It is, right? You guys nailed it, right? Because why? Because the velocity of a particle doesn't always have to be positive. And nothing would ever slow down ever, right? Nothing would ever move backwards. You wouldn't be able to reverse your car, right? That doesn't jive with reality. If the position of a particle is 0, then the velocity must be 0. No, we've shown that that's not the case, right? You can be moving at time 0. It doesn't matter. If a velocity of a particle is 0, then the acceleration must be 0. No, same deal, right? It's all about, is my position changing at that time? Is my acceleration changing at that time? Good stuff, guys. Awesome. Very good. All right. So cool. So what do we have going on here, right? So remember our example that we just used, right? We've got our position equation and we derived our velocity and acceleration equations, right? And you can see them here. I've got the one in light purple and one in dark purple, right? Because this is GCU, and if it's not in purple, then it's not an official thing. And I had to get these colors approved by the GCU color committee before I even put them in my slides. So there's a lot of hard work that I had to do here. All right, so all right, we're looking here, right? So the top graph on the left, that's my position. The middle one is my velocity, and the bottom one's my acceleration. I tried best I could to line up the times here, but they're not perfect, right? Because all of these pictures didn't get cropped at the same size, and you needed to be able to see it, right? So here's my question for you. What are the position, the velocity, and the acceleration at 2 seconds? And if you know, you can just unmute and say it. You don't have to put it in the chat or anything.
So the position at 2 seconds is 16 meters. Velocity is going 12 meters per second, and its acceleration is 0.
Oh, yep. Right, and notice a couple of things here, right? At this point, we've got a maximum velocity, right? And this is our maximum velocity. And that's going to be 0, right? So interesting. When we have a maximum, right? And this is from calculus. This is a calculus thing. So we'll knock a little rust off here, right? When we have a maximum or a minimum, we are going to have a derivative that is 0 there, right? Because at a maximum or at a minimum, we're going to assume, right, that if you were to zoom in on the top of that curve, right, it would look flat if you went super close, right? And if it's flat, there's no change. So at a max or a min, the derivative of that point is going to be 0. Okay. How about this one? All right, there you go. Note that Vmax occurs when a is equal to 0 and the slope of the velocity curve is 0 at this point. Very good. All right, clear our workspace. Let's do another one. Where are x, v, and a at t, right? What are my position, velocity, and acceleration at t is equal to 4 seconds?
So from what I can see, it'd be 4 seconds, it'd be 32 meters. Velocity would be 0. And acceleration would be -12.
Beautiful. Thank you, Zach. Yep, 32 meters, 0 meters per second, and -12 meters per second squared. And notice x is x max, right? And what happened at x max? Well, the same thing that happened at v max, right? Same thing that happened at v max. We had velocity of 0 at the max. The derivative is 0 at that point. Okay, awesome. What's the other way you can do this if you didn't have the plots, right? Well, you could just plug in those times to the equations, right, for t and solve it, right? So if I plugged in 4 to x, I would get 6 times 16 minus 54. Right? Is that right? You should get 32 out. All right, and then for velocity, right? If you plugged in 4 for velocity, right, you get 48 minus 3 times 16, which is 48. So that's going to be 48. And right, so it checks out, right? It checks out. So if you have the equation, right, you can evaluate it at whatever time you want. If you have the graph, you can do the same thing, right? They're interchangeable. All right. So that's rectilinear motion, right? Rectilinear motion, and for this class, for rectilinear motion of particles, that's where we're going to live for a while. Well, I say that for a while, but next class we're going to get into curvilinear motion and some projectile motion stuff. Just as an FYI, projectile motion is probably my favorite topic for this entire class. I used to work in firearms and projectile motion. I really like it, but we'll talk more about that next week. We have a lab activity that for next week that I think that's supposed to be next week. We'll see what happens. I'll try to make it work virtually. I don't know. I think I have a good idea of how we can do it virtually. Anyway, this has nothing to do with anything else. Do you guys have any questions on rectilinear motion? The caffeine's too much right now. It's making me ramble. Oh, in case you guys didn't see, also that's my sick coffee. All right.
So I guess one thing, so are we, with everything we're going to be doing, are we not going to be working with average velocity at all? Because this is all instantaneous from my understanding.
For the most part, yeah, we're not going to worry so much about average velocity. It's going to be, we're using the derivatives to get instantaneous velocity, right? I want to know at 7 seconds, how fast is my bullet going, right? I want to know where it is. I want to know how long it takes for me to go a certain distance, right? It's all those, it's all about, basically the name of the game is going to be instantaneous velocities here and acceleration.
Sure.
Question. Anything else? All right. So how do we determine the motion of a particle, right? Now remember, when we're talking about kinematics, right, which is what we're doing, we're talking about the geometry of our motion, right? We're talking about at a time point, I know that I've traveled this path, right? I'm trying to describe the path that a particle takes through space, right? That's what I'm trying to describe with this stuff. So generally, we have 3 classes of motion that we're going to talk about, right? Acceleration is given as a function of time, right? So A is a function of time. And we just saw that in the previous example, right? X, V, and A were all functions of time, right? So I traveled a certain amount of time and I traveled a certain distance in that time, right? Acceleration can also be given as a function of position, right? So if you weren't so concerned about how much time it took, right? But for example, you wanted to map out your commute every day, right? And you're like, well, you know what? I want to know as a function of distance from my home, how much acceleration I had. How fast was I going as a function of the distance I got away from my house? You could do that, right? You can also describe acceleration as a function of velocity. Now, most of the time, it makes the most sense to talk about these things as a function of time, right? That's the most intuitive thing, right? Some process happened for a certain amount of time, and this is the acceleration that was experienced. But, right, like in other cases, position or velocity might be what you're looking at. How are you supposed to know, right? How are you supposed to know? Well, it'll be obvious when it happens. But for the most part, most of these things are going to be a function of time. Okay. What do you guys think? A physical example of when force, right? The force applied to something is a function of position. When is force dependent on position? Good question.
Something involving like moments or something like that.
Yeah, yeah, with a moment for sure, right? But that's a moment, right? Moment is derived from a force, right? What's a specific thing that exists in the real world that the amount of force you get out depends on how much displacement you put in?
Spring.
Spring, that's the one, right? F equals kx, right? The more I push on the spring, the more force that it wants to exert, right? The more I pull on the rubber band, right, the harder it'll snap back on me, right? What about when force is a function of velocity? This one's a little trickier. What do you guys think? What is the time when force is a function of velocity?
Momentum.
Momentum is its own thing. We'll get there, but just strictly like a force, right? So if I have there's a couple of examples, right? But if I have a force, how can I get a change in force based off of how fast something is moving? The real world, there's real world objects, right? No. All right. Let's see. Any other guesses?
Not a moving car.
I'm sorry, Julian, say that one more time. I cut out.
Because we're on force as a function of velocity, right?
Yeah, I didn't hear what you said the first time. So.
Okay, so why not a moving car or something, like how fast the car is going? I know it's just speed, but it's also got a direction, so it would be the velocity.
Sure.
I mean, the force is based on mass times accelerate, or yeah.
And so the faster you're going, the more force you exert. It's not entirely wrong. I like where your head's at. I was thinking, and it is something related to cars, drag, right? The amount of aerodynamic drag that you see increases the faster that you're going, right? There's also dampers, right? So you guys, I'm assuming everybody here has experience with a screen door, right? And you know how it has that sweet door closer on it that won't allow you to slam the door? That's a damper, right? And what that does is it pushes a bunch of air through a plunger, through an orifice plate with a plunger, right? And the faster you push on that, the more it's going to resist being moved, right? So if you have a screen door on your home right now, wait till after class. Don't go right now, but wait till after class and try to slam it as hard as you can. See what happens. Okay. So here's a table that we're going to fill out, right? So what do we have here, right? In the first column, we have if. If acceleration is a function of time, what happens? We get a kinematic relationship, right? dv dt is equal to a of t, right? So we can say that if acceleration is a function of time, then that's just the derivative of my velocity with respect to time. And if I integrate that, right? If I integrate that, I would get this expression here, right? Well, why would you want to integrate that? Well, if I want the velocity, right, then, well, I need to integrate it. Okay. And I know that you guys have not had differential equations, right? And this is kind of a little bit like that, right? So what are we doing here, right? So if you wanted to solve this for velocity, what would you have to do? Well, you'd have to multiply both sides by dt, right? This is called separation of variables. Now, everything that's a function of time, both of these are, all right. So now everything that's a function of time is on one side and everything that's not is on the other, right? Because dv is not a function of time. It's just, think of that as delta v, right? And so you're going to integrate that from your initial velocity to some velocity final. And you're going to integrate the other side from 0 to some time t. All right. Now, that's all well and good, right? That's all well and good. Let's keep going. Right? What if I have a function of position, right? Acceleration is a function of position. Well, if acceleration is a function of position, I know that this dt is equal to dx over dv. Well, how do you know that, Dr. D? That's a great question. Well, this is just rearranging v is equal to dx dt, right? V is the derivative of position with respect to time. So I'm just rearranging things to get dt in terms of something. And I know acceleration is a function of dv dt, right? And so now for time, I made dt, I made time a function of x, right? So it's dx over dv, and I can plug that in to my equation where a is, right? And I'll get v dv is equal to a of x dx. And you can do a similar thing with your integration on the other column, right? And then finally, what if acceleration is a function of velocity? Well, then dv dt is equal to acceleration as a function of velocity, right? And you can separate your variables like that, or you can do it similar to what we did above there and say v dv dx is equal to a of v, right? And separate your variables. When do you need to do this, right? This is for the general case. Whenever you have kinematics in general, you have to use this. I will post in LoudCloud tonight, either tonight or Monday morning, a handout for you guys that has a bunch of kinematic equations on it, right? And we can talk about that on Wednesday next week, right? And essentially what it is it's going to be a useful thing for us to use, right? And you'll see why in a second, right? Because this is the general case. And I know you're all thinking, well, you said, Dr. G, that we wouldn't have to do very much integration, but this table is all about integration, right? And that's true. It is on there. So am I a liar? Well, not necessarily. But before we get into why I'm not a liar, let's try one here, right? So we'll do this one together, and I'm gonna see if I can't cut some of these lights and actually use the light. That should be a little bit better. Should be a little less glare on that now. You guys let me know if you can see this, okay? So what do we've got here, right? The motion of a particle is defined by this relationship. X is equal to 6 t to the fourth, right? So you guys are gonna have to, I'm gonna write this down, then I will unshare the screen and you tell me if you can see it, or you can pin my video, one or the other. I am very doubtful that you will be able to see this. It's pretty glareful, pretty glary. My markers aren't apparently that good on this whiteboard. Can you guys see this at all? Is this a waste of my time?
It's not bad.
I can see it.
Okay. All right, so you can see that this says x is equal to 6 t to the fourth minus 2t cubed minus 12t squared plus 3t plus 3. All right, we want to find the acceleration we want to find the time, position, and velocity when when acceleration is equal to 1 meter per second, right? Squared. 1 meter per second. Is that color okay? Can you guys see that color? You know what? I'm gonna unshare my screen real quick. maybe not. There we go. Okay,
Yeah, that's much better.
it's not often. Okay, so we're gonna do this, right? So how do we do this? Right, well, I was given this acceleration. I better take the derivative of this a couple times, right? Because I need to figure out what the acceleration is. All right, so let's do that. I'll take the derivative here a couple of times, right? So my velocity is going to be equal to 24 t to the third minus 6 t squared minus 24 times t plus 3, right? Is that everybody in agreement that that looks okay? Did I botch it completely? Yeah, it looks okay. I'm gonna think that if nobody answers me, then we're doing all right.
It doesn't look that bad, actually. It's a little low quality just because of the camera, but other than that, you can actually see it fairly decently clear.
Yeah, I think maybe I'll just try to make sure that says 1 by acceleration.
Yes.
1 meter
Yeah.
per second squared.
I can play with the focus a little. I don't think that changed anything. Okay. So that's that. So now we're gonna take the derivative of that again, right? We take the derivative of that again, and we get what? We get 72 t squared minus 12 t minus 24, right? Okay. All right, so what were we asked to find, right? Well, we were asked to find we want to find the time, we want to find the position, and the velocity. Okay. So we want to find time, position, and velocity. So I'm going to take this equation for A. And I'm going to say, well, I'm going to figure out what time. I'm going to solve it for time, right? Because I know that the acceleration is 1 meter per second here. Right? So if I plug in 1 here, right, I will get 1 is equal to 72 t squared minus 12 t minus 24. And then I have to solve this equation, right? So how am I supposed to solve that equation? Well, you can use the quadratic formula if you want, or you can do what I like to do, which is you can throw it into your calculator, right? And tell your calculator to solve it for you, right? Which is perfectly fine when we're doing quizzes, if that's the method you want to do. You could do it, you could add 24 over and then factor out a t, right? And you can do all that stuff. You can do it the long way too, right? With it, it's algebra, right? So if you solve this, you'll get what? You'll get 2 answers for t, right? Because it's a quadratic, right? Because it's a square, you're gonna get 2 answers. You'll get t is equal to 0.678 seconds, and t is equal to negative 0.512 seconds. All right, so you got that, you solved this, and that's the answers that you got, right? Which one of these is the answer?
Positive.
The positive. Why?
Because you can't have negative time.
Well, you can, as long as you have a TARDIS or a flux capacitor, but otherwise it's not possible.
Or whatever Bill and Ted had.
Sure, phone booth. That's right. Look, let's all make an agreement right now if any of us invent time travel, we will show up in this room right now, 1:17 p.m. on 9/11/2020. All right.
Arizona Standard Time, right?
Yeah, of course.
Intriguing.
I guess not. All right. So it's the positive. It's gonna be the positive one. Yes, it's gonna be the positive one. All right. All right. So now we've got the acceleration, right? Or I'm sorry, we've got the time. So we can cross time off our list. We did it. Great. Good for us, right? So now what? Well, now we come back up here to this velocity equation. What do I have in here? Well, I just have time, right? So I can plug in 0.678 seconds into this equation, right? So I plug 0.678 seconds in here. Okay, so let me write this down over here so I can erase what we just found out, right? So we find that t is equal to 0.678 seconds. Okay. All right. So let's plug that into here, right? So I've got my velocity equal to 24 times 0.678 cubed, right? Minus 6 times 0.678 squared. Marker dying. Next marker. Try that again. 24 times 0.678 cubed minus 6 times 0.678 squared minus 24 times 0.678 plus 3, right? And obviously, without having to use a calculator, we can all see that that is obviously negative 8.55 meters per second. Okay, negative 8.55 meters per second. That's velocity. All right, and so if you guys said, well, hey, I think I'm picking up what you're putting down. So now I'm going to take that time and I'm going to plug it in to my equation for x. Well, you got it, right? You got it. So what do we have? X is equal to 6 times 0.678 to the fourth minus 2 times 0.678 cubed minus 12 times 0.678 squared plus 3 times 0.678 plus 3. Right? And so what is x? Well, we plug it and we chug it, and we find that x is equal to 0.162 meters. Okay. So what did we have to do to figure this problem out, right? What did we have to do? Well, we had to do the derivative twice. And we had to do the derivative twice. You guys have any questions on that problem? Right. If you're given the expression, right, then you can just take the derivative, right? With a polynomial like this, right, that's split out like how this one is, it's not horrible to take the derivative. It's not horrible. Okay. Questions on this? No, everybody's okay.
I guess it's been quite a while since I've done like quadratics with like those kind of numbers involved. Were you just using some sort of calculation, or did you come to that conclusion?
For which one? How do I solve the first equation for time? Is that what you're asking?
Yeah, like once you got to acceleration.
Yeah, so I put it in my calculator, right? And told it to solve it. But if you don't know how to do that, right? You can always, hold on, wait for it. I'm gonna share screen in a second. You can always use this. I'm gonna share this, right? Maybe not. You can always use this. All right, quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2 times a, right? So if we looked at, well, I don't have it up here anymore, right? But our equation for acceleration was 72t squared minus 12t minus 24, right? Where 72 was a, negative 12 was b, and negative 24 was c.
Okay, yeah. That brings back memories. Thank you.
Yep. No problem. All right, any other questions? Okay. All right, so here's another one. I want you guys to take some time and try this. Okay? The velocity of a particle is defined by the relation of the motion of the particle. No, I don't know why that's there. So all right. The relation of the particle is defined. The motion of the particle is defined by the relation v is equal to t cubed minus 56t squared minus 20t minus 700, where v and t are expressed in meters and seconds respectively, meters per second and seconds. Determine the time, velocity, and acceleration when the position is 205 meters. Okay. So you guys take some time, work on that. You know what? You know what? We're not gonna do that right now. Yeah, so take some time. Let's say we'll start off 20 minutes. I'll give you guys to see what we can do. And if we need more time, we have more time. All right, so I'll be here. If you have questions, let me know. I will just be hanging. You guys still see the screen?
What was that about?
Hmm?
I just got like a dialogue box. Host would like you to unmute.
That's weird. I didn't do any of that. We got
Alright,
hacked, man. We got hacked. Everybody,
I'm
get
shutting
desk,
down.
under your desk, quick.
Just quick question. So when we for this, or not to spoil anything, but we'd have to do an integral to get back to the x function. How do we work with the c? Because we normally do like a plus c or
Ah,
plus.
yes. Very good question. Just assume that just assume that it's 0 for now.
Okay.
That's what we'll do.
Okay.
But normally I'd have to give you some kind of bounds, right? But for right now, we'll just assume that the initial condition makes it such that C is 0. How we doing? We're doing all right?
What does the bottom of your shirt say?
It says everything I say will be on the exam,
Crap.
including that.
Oh, I was about to say, should I write that down?
So when we find the time, we plug it back into the position equation, right?
Yep. Find the time and then you're gonna plug it back into the velocity and the acceleration equations.
Okay.
You're gonna use the position equation to get the time. Everybody doing all right? Anybody want more time? All right, who wants more time? Nobody? Everybody? I meant for this problem, not just like in general. Obviously, everybody wants more time in general. Yeah. Okay. Nobody wants more time? No, we good? All right, let's bring it back then. So what do we do? I think based on the questions that you guys were asking and some of the things that people had asked in the chat, right? Based on some of the things that people had asked in the chat, you guys were on the right track, right? It's basically very similar to the problem that I just did before this, except that instead of us having the position and taking the derivative all the way down, we had almost the worst case scenario where we had to take one integral and one derivative, right? The worst case scenario being I gave you the acceleration and you had to do two integrals to get back, right? And I didn't give you any initial conditions, which could have complicated things, but you know, we just assumed that we were running at the initial condition where C is equal to 0, then we're fine. Okay, great. So what do we have, right? How do we do this? Stop sharing. All right, so you can see here, I've got my initial equation. And if I want to go up to position, you can see I have my derivative sign here. If I want to, or my integral sign here. If I want to go down to acceleration, I have to take the derivative, right? So let's do this, right? We'll do the acceleration first, right? That's going to be 3t squared minus 112t minus 20, right? Nailed it. Or if we take the integral to get to position, we'll end up with 1/4, sorry, t to the 4th, minus 18.7 t cubed minus 10 t squared minus 700 t. Okay. So this one is a little bit, this one's going to be a little bit trickier to solve, right? Because unlike the last one, we don't have a nice quadratic. And I see that we can't see the top of that anyway, so I shouldn't write that high. Because nobody can see that at all. Perfect. Just the way that I want. I could have written anything up there. You guys would never know. Never know. That's exactly how we want it to work. Excuse me. Okay, so just so you guys all know, the top line up here, what this says is x is equal to 1/4 t to the fourth minus 18.7 t cubed minus 10 t squared minus 700 t. That's what it says. Should be plus c, but we're assuming that c is 0, so that's fine. What are we going to do here, right? What are we going to do here? Well, we're going to take this x equation and we're going to put, for some reason I wrote 250 there, it's 205, right? We're going to put 205 meters in and we're going to solve for t, right? All right, so if you use your favorite solving program like Wolfram Alpha or your TI-83 or whatever calculator you have, right? We can solve this equation for 205. And how are we going to do that? Well, what happens? What do we get out of it? We find that we get 75.817 seconds when we solve this, right? So time is equal to 75.817 seconds. How many decimal places should you keep? Personally, I would keep all of them in your calculator and run through all the numbers and then bring it down to like 2, for most cases, 2 decimal places. You'll see in a second that it's really going to be really important for the answer that we got, that we keep as many decimals as possible when we plug this value in, right? So how did I solve this? Legit, I'm going to tell you, I used wolframalpha.com and I put it in there and I solved it that way. If you don't want to do that, that's fine. You can do algebra, right? How would you do algebra with this? Well, it's a 4th order equation, so you can break it into 2 second order equations, right? And that would mean you'd have 2 quadratics, so you have to do some algebra, split it apart into 2 quadratics, and then you use the quadratic formula to solve each portion.
No, what did you get for t again?
75.817 seconds. That is what we're working with. Okay. So then I take that 75 seconds, almost 76 seconds, and I plug that in. Let's plug it into the velocity, right? So let's think about this for a second. What is this result telling us, right? What is this result telling us? This is telling us that it takes us 75 seconds to go 205 meters, right? That's almost 700 feet in 75 seconds, right? So that's 75. Let's just do, let's just say it's 750. I know it's not 750 feet, right? But let's just, for the sake of math, 750 feet in 75 seconds. That means we're traveling roughly at what, like 100 feet per second, something like that. It's pretty fast. Okay, pretty fast. And it turns out that instantaneously at this point in time, our velocity is 111,696 meters per second. I'm sorry, 111,696.09 meters per second, because that 0.09 is really going to put us over the edge on this one. So it's traveling at a pretty good clip. Okay, it's traveling at a pretty good clip. And if we plug in this time for our acceleration, we'll get 8,733.15 meters per second squared. How did you guys feel about that problem?
I think I need to get tutored in quadratics again.
What's that?
So I think I need to take
Oh.
quadratics again.
All right. That's how some of these work, right? These integration and derivative problems, right? And now remember, these are not uniform. These are not uniform problems, right? These are variable velocities and variable accelerations. There's a very specific case that we're going to talk about in a minute, right? That is for uniform stuff. Maybe we'll come back. Oh, shoot. Shoots and ladders. What happened? Something happened. Sorry guys, I lost my slideshow. So scared, you know. Nope. There we go. Okay, so let's do, can you guys see the screen? I'm gonna do one more. You guys will work on this. It says work alone. I'm gonna put you back in your groups. I unfortunately don't have my sheet with me, so refresh my memory. Who was in what group, right? Captain Crunch. Who was in Captain Crunchitizers or whatever it was called? Julian, Steve, Zach. Were you in that one?
Yeah.
I think there was one more. Who was the last one?
It was
I was
me,
in that.
It was me, Zach, Nathan, and Julian.
I was in I don't care.
Oh, never mind.
It was me, Connor.
Oh yeah. Whoops.
Then we've got the Latin. I don't care. Right? It was Nathan,
Yeah.
Logan, and
Miguel.
yeah. And then there was we're tired. Brandon, Mauricio, Alexis. All right. Cool. I'm going to put you guys in breakout rooms. You can have 30 minutes to solve the following problem. I will put it on the board. All right. First group done. You guys can get a prize. If you need me to come in and talk to you about how to do this stuff, you can raise your hand or call me in, and I'll come in and make a lot of noise and hopefully answer your question. All right. So here's the problem. Right. I've got a mountain bike shock. It's used to provide shock absorption. It consists of a piston that travels in an oil-filled cylinder. As the cylinder is given an initial velocity V naught, the piston moves and oil is forced through orifices in the piston, causing the piston cylinder to decelerate at a rate proportional to the velocity. You need to determine the velocity, the position as a function of time, and the velocity as a function of position. So you guys copy this down so that you have it. I'll put you in breakout rooms, and then before we go, I'm going to put that table that we used earlier back up on the screen. Okay. All right. So I got those ready. All right. So you guys know what you got to do. You got a picture of it and everything. Okay. Let me throw this back up. You might want to grab a screenshot of this. It's going to be helpful. This is going to be helpful. So here's the question that everybody's gonna ask. On a quiz, do we need to remember this, right? Or will we have this available? Well, glad you asked because I kind of covered it at the beginning of class. I'll talk about it again right now. What you are gonna have for the quiz is your kinematic equation sheet that I'm gonna post on LoudCloud either today or Monday morning, okay? And you'll be able to use that on the quiz. Also on quizzes, the final sheet will be a relative or a relative. The final sheet will be a relevant equation list of things that I don't expect you to memorize, right? In the real world, if you ever need to use these equations, you will know where to look them up. You don't have to memorize these. Don't waste time memorizing this stuff, okay? All right, everybody's got this and the other thing, right? Are we good to go? I'm gonna hit open all rooms. All right, you guys get 30 minutes. Oh, yeah, we're good. 30 minutes, go.
Did you take that picture, Brandon?
Yes, I did. It was in Zion National Park.
Or like what hike is that in Zion? Is that Angel's Landing?
Yes, it was.
Okay, cool. I was there like a week ago.
Alrighty.
Oh, it's beautiful, isn't it?
All right, so we're just gonna break it now, and we're gonna talk about it. Everybody was right there, right around the same spot. So good job. Not sure what the prize was. If you guys were in class, I would bribe you with, candy and snacks and things. But I brought snacks to my classes yesterday. Nobody took any. It was really rude. It's a joke because nobody's there. I'm so lonely. Anyway. Okay. So how do we do this? You guys were all on the right track. It was looking good. So the first step here, right? Here we go. We know A is equal to negative KV. We're talking about the black text first here. Okay, the black text. So A is equal to negative KV. This, as you all recognize, was a function of velocity, meaning that when we looked at that table, we needed to use acceleration as a function of velocity, which we can rewrite as dv dt is equal to negative kv, or we rearrange this, we end up with 1 over v dv is equal to negative k dt, right? K is a constant, does not matter which side you put it on or where. I left it there just because it's a little bit nicer in the end, and you're gonna wanna bring it over to the time piece anyway, as we'll see in a sec, right? So I'm gonna integrate this, right? And I'll end up with the integral from v naught to v of 1 over v dv is equal to negative k times the integral from 0 to some time t dt. Okay. Well, turns out that if, and I'm going to stop my share for a second, if you have something that looks like that, you'll have the natural log of v minus the natural log of v naught is equal to negative k times t, right? Well, there's the property of natural logs here, right? If I subtract these, right? If I subtract one natural log from another, what do I end up with? Well, I'll end up with ln of v over v naught. I can simplify this down into this, okay? And that is equal to negative kt. The next thing we're going to do here is we're going to take everything and put it up. So we're going to use e to the power of everything, right? Because why? Because e to the ln, right? This becomes 1, and I'll be left with v over v naught is equal to e to the negative kt, which I can say, well, v of t is equal to my initial velocity times e to the negative kt. What if you didn't do this part, right? What if I didn't recombine those? Well, if you didn't recombine them, it's not the end of the world, but you'd end up with this anyway because of the way that e works, right? Because of the way that e works. All right, cool. Get rid of that. I'll share the screen again, so you guys can take a look at that. All right. Cool. Everybody, we were right there, right? And so what's the next part of this, right? We needed the velocity or the position as a function of time. Well, now we have the velocity as a function of time, right? And that's just equal to dx dt. So I'm going to take this equation and I'm going to say, well, dx dt is equal to v naught e to the negative kt, right? And I'm going to do the same thing that I did the last time, right? And this should say here, from the integral from 0 to x dx is equal to v naught, because v naught is a constant. That's my initial velocity. That's a constant to my system. The integral from 0 to t e to the negative kt. This should have a dt on the back end, right? That should have a dt. that turned out way better than I thought it was going to. Excuse me. Right, so dt. I take the integral there again. Well, the easy side right here, the integral of x of dx from 0 to x is just x of t. Right, on the other side, what do we get? Well, v naught stays there. Well, if I take the integral of e to the negative kt, well, that's going to just mean you can use antiderivatives here. Look it up in your integral table, right? If you were to take the derivative, you would just pull the k down, right? But since it's the antiderivative, it's negative 1 over k, e to the negative kt. And this line here means I'm going to evaluate it between 0 and t. What am I evaluating? The variable t. So what am I left with? Well, if I plug in t, right, I just get this. Well, I'm going to pull this 1 over k out because that's a constant, right? So that'll come out. So I'll have v naught over k. I'll have negative e to the negative kt, right, minus e to the 0. So that's just negative 1 over k. And so I'll end up, after algebra, with x of t is equal to v naught over k times the quantity 1 minus e to the negative kt. Okay. Does everybody kind of see where this one comes from? This one's a little trickier, right? The other one's a little more straightforward, and you're probably all like, this is calc stuff that I do not remember. And I get that. It's been a while for everybody. It's fine, right? These are probably, this one is probably on the scale of, on the hardness scale of problems you'll see in this class for integration. This is probably where it's at, right? You had to do natural log and you had to do E, right? That's going to be the hardest ones. All right, you guys have any questions on these two parts? Because there's one more part, right? We need, what did we need? Let me remember. We needed velocity as a function of position as well. Anybody have any questions? Everybody okay here? Yeah, we good? All right. Well, moving on to this then. Acceleration as a function of velocity, right? So I've got to start here, right? Because I need something in terms of the velocity in terms of x, right? Okay, so acceleration is velocity times the change in velocity with respect to position. Where did that come from? All right, let me draw my drawings. So where did that come from? Let's look here. Well, hey, that's the very bottom row here on our table, right? V dv dx is equal to a times v. So this is all we're doing. All right, we're going to do this, and we're going to use this integral here. All right, and so if we do that and we use this integral, right, you end up with negative 1 over k dv is equal to dx, right? Well, take the integral again. Look, this one is a bit simpler than the original one we did, right? Because we're left with something that is solely a function of our velocity on one side and then just dx on the other. So we end up with v of x is equal to v naught minus x times k, or k times x. Okay. And that's it. Again, this one is definitely the hardest one that we did all day, I hope. Right? I hope you guys agree with that. We kind of built up to this one today, right? You guys have any questions on this? This is the whole reason why integrals and derivatives are important, but we're going to go over in a minute.
I have a lot of questions.
Okay. You want?
Can I save it for after class?
Sure.
Just letting you know.
All right. All right. So this is the general case, right? This is very general. We don't know a lot of information about our system, but we can get velocities and accelerations and as functions of different things, right? But what happens in a very special case when we have uniform rectilinear motion, right? Well, what do I mean by that? Well, I don't mean that it's uniform. I mean that it's uniformly accelerated. Okay, so we have a constant acceleration, right? So for a particle in uniform acceleration, it's accelerating at a constant rate, right? So you can recognize these constant acceleration equations from your physics book, right? These are the kinematic equations from physics, right? And this is just saying that dv dt is equal to a is equal to constant. And so if you do that integration that we had earlier, you'll just be left with v is equal to the initial velocity plus acceleration times time, okay? And I'm going to give you guys a sheet on Monday for Wednesday's class with all this information on it, right? We can get an equation for position that's based on my initial position, my initial velocity, and the acceleration. And we can even do this one, right, where we have velocity as a function of acceleration and position. Now you need to be careful with these because they only apply if we have something under uniform acceleration, right? So how do we know if we have something that's uniformly accelerated, right? Well, if they tell you that it's a constant acceleration, that's a big keyword, right? That means it's uniformly accelerated, it's constant. If they say you're running at a constant velocity, well, that's a constant acceleration too, because a constant velocity means that you have a zero acceleration, right? Because your velocity is not changing, right? And I want you to notice something. If you use that position, right, that distance equation, x is equal to x naught plus v naught t, if you're running at a constant acceleration or a constant velocity, right, zero acceleration, you get x is equal to x naught plus v naught t, right? So this goes away at a constant velocity. Okay, well, isn't that just distance is equal to my initial position plus my rate times time? That's just distance equals rate times time, right? So just keep that in mind, right? These are all, you should be pretty familiar with some of these. Okay. If I were you, well, you know what, I'm going to do the next example. You guys have any questions on this? Again, you'll have all these equations when we are doing our doing homeworks and quizzes and things, right? Okay. I don't expect you guys to memorize these at all.
Thank you.
What's up?
I just wanted to say thank you.
No problem. All right, so let's do an example here, right? All right, so you're stressed and you need to work out, but unfortunately all of the gyms on campus are closed because thanks COVID, right? So you decide to run in the neighborhood surrounding GCU. You're jogging at a 10-mile-per-hour pace for about 15 minutes when you notice this big dog starts eyeing you up. Deciding to not take any chances, you start to sprint with a constant acceleration of 5 feet per second squared. How far did you make it in the first 15 minutes of your jog? All right, and we're going to report the answer in feet. And how long did it take us to get back to campus? All right, so as a quick out and back, right? A quick out and back. All right, so how do we do this, right? Well, start off with some unit conversion, right? Because we need those unit conversions. Right? So I need to get from 10 miles per hour into something that gives me feet, right? And that means either getting it into feet per minute or feet per second. Personally, I prefer getting things into feet per second, right? So 10 miles per hour is roughly 14.667 feet per second. And what is that? Well, that's our velocity, right? And we're going to assume that it's a constant velocity, right? Why? Because it says we're running at a 10-mile-per-hour pace, right? And our average velocity over our jog would have been 10 miles per hour. So we're just going to assume that it was constantly 10 miles per hour. We need to convert 15 minutes into seconds, which is 900 seconds, right? You guys, please check my unit conversions if you want. Highly recommend. Okay, well, that's cool. Well, let's go back for a second, because what were we asked? We're asked how far did we make it in the first 15 minutes, right? So before we decided to turn around to escape the clutches of the dog that was eyeing us up. All right, so we're running at a constant velocity, which means we have a constant acceleration of 0. We want position, so we're going to use this equation. X is equal to x naught plus v naught t plus 1/2 at squared, right? For a constant velocity, that's the equation, or a constant acceleration, that's the equation that gives us position, right? We're going to assume that we started, right? So what is x naught, right? X naught is our starting position, right? It's our starting position. Another way of thinking about this, right, is if I write this equation down this way, right? X minus x naught is equal to v naught t plus 1/2 at squared, right? Why would I want to write it like this? Well, x minus x naught is just our change in distance, right? It's going to give us the total distance that we traveled, right? In our case, another way of thinking about this is I'm going to assume that x naught is 0. I started at campus, I started at 0, and I ran some distance, right? So we're going to assume that that's 0. So I'm going to stop sharing my screen. We're going to use that equation, right? We use that equation. So using that equation, right? Remember, our initial velocity was 10 miles per hour. And I wrote it in the spot where you guys aren't going to be able to read it, which is equal to 14.667 feet per second. And 15 minutes is equal to 900 seconds, right? And the equation that we're interested in using is x is equal to x naught plus v naught t plus 1/2 at squared. Okay. All right. So in our case, we're going to say, you know what? My initial position is 0. I started at the starting line, and I'm saying that the starting line is 0. In our case, we're at a constant velocity, so our acceleration is 0. Our acceleration is the rate of change of our velocity. If our velocity is not changing, then the acceleration is 0, right? So I'm left with x is equal to v naught times t. Okay, well, that's 14.667 seconds. Oh, sorry, not seconds. Times 15 minutes times 900, right? So x is 13,200.3 feet. Right. Which is what? It's roughly 2.5 miles. So you went 2.5 miles in 15 minutes, which for me, that's a really good pace, because I'm pretty sure I would drop dead, but you know, that's me. I'm not as fit as I once was. I'm getting old.
Is that a time in seconds?
That time, 900, is in seconds, yeah.
Okay.
Yeah, right, because look, I've got this in feet per second. I've got this in seconds, so that'll give me out, right? And I was asked specifically when we were in the problem statement, right, to do that in feet.
Can you throw the original problem up there one more time?
Yep. I guess. So demanding, geez. Okay, so that's the first part, right? How far did we go in that first 15 minutes, right? 2.5 miles. Okay. So how long did it take us to get back to campus? So now we're 2.5 miles away from campus. And this dog starts eyeing us up. So we're gonna haul, right? We're not gonna take any chances. We're just gonna haul back, right? And we're gonna accelerate at 5 feet per second squared all the way back, constant acceleration, right? Not stopping for anything on the way back. So how long did it take us? Well, we're gonna use the same equation. We're gonna use the same equation here. Okay, so again, this time I'm gonna set some different parameters. What do I know? Acceleration is 5 feet per second squared. All right, can you guys see my video now, or is it still the screen?
It's still the question. I can't really see your screen all that well.
Cool. Just checking. Okay. So my acceleration is 5 feet per second, right? Five feet per second squared. I am a distance of 13,200.3 feet from campus, which means that I know that my final distance that I have to travel is 13,200.3 feet, right? So whether you put this as x is equal to 13,200.3 or x naught is negative 13,200.3, it doesn't matter, right? So I'm going to say that I'm going to break this problem apart, right? I'm going to say the first half is done. Now I'm starting again, and I'm saying that my starting line is where I'm starting, and that's going to be 0. And I know I have to go 13,200.3 feet away, right? And so I can use my equation again. X is equal to x naught plus v naught t plus 1/2 a t squared. Right? It's 1/2 a t squared. This guy is going to be 0. Well, what's v naught? Well, we were running at 10 miles per hour, right? We were running at 10 miles per hour when we started this. We saw the dog, so that's our v naught. We're still running at 10 miles per hour when we start. We won't be running at that when we finish, but that wasn't what the question asked us for. Okay, so I've got everything I need, right? I've got my acceleration, I've got my velocity, I've got my position. I can solve this for time. So what am I going to do? Well, I'm going to have 13,200.3 is equal to 14.667 times time plus 1/2 times 5 times time squared, right? Well, that's a quadratic. We use the quadratic formula, or we can use our calculator, and you will get time is equal to 69.79 seconds for negative 75.66 seconds, which, as we discussed earlier, and since nobody came back to let us know, this is not the answer, right? Because it's negative and would imply time travel. But instead, we found that we ran 2.5 miles in about 70 seconds. So should go try out for the Olympics, because it's pretty quick. You guys,
Outstanding.
yeah. again, you were under duress, right? I mean, little old ladies can lift up cars when babies are in trouble. So there's that. Okay. Do you guys have any questions about this problem? Are these all that easy? No. Are they hard, much harder? Not really. What happens with constant acceleration problems, right? With uniformly accelerated particles, it's all about how you break down the problem, right? What do you know? What do you need to find out? The equation sheet that I will give you, where is it? I have a copy of one that's similar to it here. Let's see if you guys can, I'll stop sharing so we can see into this. It looks kind of like this. It's laid out slightly differently, right? You can see here it says acceleration, and then it gives you, when I have this variable, these variables, I should use this equation, right? Your equation sheet is not a table like this, but it has sections saying, if I have these variables, then these are the equations I should use, right? So it breaks it down pretty nicely. And it's very situational, okay? You can define these equations by any variables really. But you know, I'll give that, send that out to you guys later. All right. Do you guys have any questions? Comments? Pretty good.
A side comment, I thought it was intriguing how that last question depicted the surrounding areas of GCU.
You know, I did my best.
Very well put.
I tried to make it something that was, you know, real life for everybody.
Something we could more easily relate to.
Exactly.
Or that, or like a almost man chasing us.
You know, it's late at night and you go to the Jack in the Box, right? And you got to get home, right? That's how it is. All right, cool. All right, so that's it. That's all I got for today. It's Friday. We'll end a little bit early. I don't think anybody will complain. Let me know what you guys thought was the most confusing thing about today's class. All right. That's it. Have a great weekend. Once you fill this out, you can go if you want. But have a great weekend, and I will see you guys on Wednesday. All right. See you guys on Wednesday.